Hello YouTube and welcome back to this edition of numerical analysis, and we're going to be talking about limits, continuity, and numerical theorems within this video. So with that being said, let's get right into it. So we're going to talk about what a limit is and what a continuity is, and for majority of this course I'm going to be explaining the concepts rather than the actual definitions, because I feel like when you understand the concept behind a term, then you will be able to understand the definition quite easily. So I'm going to be wording things a little bit different to help you understand what this concept actually means or what something actually is. So with that being said, let's get into it. So what is a continuity? Well, a continuity of a function is defined as the continuous formation of f of x. It is never ending and does not have any jumps or holes in it. Well, this is not the actual definition of what a continuity is, though this is just basically what it is as a concept. Basically, if you have a graph that is continuous, has no asymptotes in it, and it just keeps on going and going and going and going, then you have a continuous function. In simpler terms, if f is continuous, it means whatever values of x you place, f of x will always be valid. These functions have no restrictions throughout their domain or given interval. Let me give you a visual representation for what I mean. So we have a function f of x is equal to x, right? So this is a linear function. We know this. And linear function go in this format. So they keep on going and going and going. So for whatever value of f of x you plug in, for whatever value of x, f of x will always be valid. So you can put negative infinity and on x, and you have f of x which will also be equal to negative infinity, and so on and so forth, right? You have this type of relationship there. And let's say you have a quadratic equation where x has got the power of 2, and it goes something like this. And for every value of x that you plug in to f of x, it will always be valid, and there is at no point within this graph will this graph be invalid. So you can plug in negative infinity and you will have positive infinity throughout, and so on and so forth. And you have a polynomial function, right, where x is to the power n. It could be 3, it could be 4, it could be 5, it could be 6, so on and so forth. And you will have this type of graph, and it will continue going and going and going and going. For every value of x that you plug in, it will always be valid. It will not have any point within the function where it is undefined. That is what you call continuity. And basically, if you just have a function that keeps on going and going and going, you have a continuous function. Keep that in mind. This is the definition, or this is the concept behind continuity. So we're going to talk about what a limit is. With understanding what a continuity is, we're going to talk about what a limit is. So a limit to a function determines or allows the observation of the behavior of f of x as it approaches a predefined value. What that means is it allows us to observe how the function operates, or what the function actually does when it reaches this value. So we're just looking at it and saying, hey, what if I plug in 1 into this function? What will it do? Or if I plug in infinity, what am I going to do? This is just hypothetical, but that's what the limit actually is. The concept behind the limit is to be able to see or to observe the function as we approach a certain value. Let me give you a visual representation. So we have this type of graph, right? And then let's look at f of x is equal to the square root of x, right? So we know that we cannot have a negative value in x because it will give us an imaginary number. So meaning we do have a function that goes in this format. It might not be exactly to scale, but it is something in this format. As we can see that if we plug in any negative number into this square root function, we will get an undefined value. So meaning if x approaches infinity from the left hand side, meaning going this side, we are going to get an undefined value for whatever iteration or for whatever point we are going to plug in x. So if we put in -1, this value will be undefined. If we plug in -2, and so on and so forth. But notice that if we plug in 0, we have a defined value because the square root of 0 is just 0. So meaning the interval for this function here, or the range, or whatever you might call it, starts from 0 all the way to positive infinity. All those values are valid. So we get this kind of relationship where we see or observe the function as we plug in certain values. If we plug in -1, we get an undefined value. If we plug in 1, we get a value at that point there, at what f of x is at that point, or for whatever reason, or for whatever value that is. So I hope by now you get the basic idea of what a limit is and what a continuity is. So if we do have an interval between 1 and 2, we're going to say that this function is continuous within the interval, that point, because this function has no asymptotes in it. So there is no point within this interval 1, 2 where this function is undefined. Whereas if we were to say the interval between 1 and -1, this is not a continuous function because at this point here between 0 and -1, we have an undefined region, and then at this point and this point we have a defined region. So it's not basically continuous because it ends at some point, and we do have a limit at some point as well. So that's the relationship between a limit and a continuity. Hope that makes a lot of sense. So I hope that helps us understand the difference between continuity and the limit and how they are connected and how they relate to each other. Okay, so now with the concept understood, let's go to the actual definition in numerical analysis, right? So limits, the definition of a limit is a function f of x is defined within a set x that consists of real numbers and has the limit L at x naught, written as limit as x approaches x naught for f of x is equal to L. A few things here before we proceed into all these other definitions and all that. When we talk about x naught, we talk about x naught, x1, x2, x3. Basically, we're talking about the iterations of x, the values that we start with. Some of the tutors will tell you it starts from x1, x2, x3, x4. Others will say x naught, x1, x2, x3. They're basically the same. It means that the values are basically starting from 0 or 1. So depending on who taught you, or depending on who taught you in grade school or anything, we start our index from either 1 or 0. But what that basically means is just the initial iteration of our x values. So let's just say if we have an initial x value as 0, so our x naught will be actually equal to 0. I hope you get the picture. X naught are basically iterations, or let's just say it's basically an index where it starts from 0, 1, 2, 3, 4, and these are our initial values. So x naught is an initial value, x1 is our second value, x2 is our third value, and so on and so forth. So for the majority of this video, we're going to be using the notation of x naught, x1, x2, x3, and so on and so forth. So I hope that doesn't confuse you later on in the videos. Okay, so let's go back to our actual definition. So given any real number represented by epsilon, if epsilon is greater than 0, meaning if it's positive, there exists a real number, delta, which is also greater than 0, where epsilon exists on the y-axis and delta exists on the x-axis, and such that the absolute value of f of x minus the limit itself is less than the epsilon value whenever the value of x is a member of the set x of real numbers, and the value x minus an initial point of x is also less than delta. This is just the definition in case your lecturer asks, say, define what the limit is, causing in numerical analysis and whatnot and whatnot. You can use this definition because it's the definition that is universally known and which is a numerical analysis. Don't get scared or anything or intimidated, say, no, this and that and this and that. When, in short, this is just all fancy work. All you have to do is master what this is, and yeah, you write it down when the lecturer requires it. So let's just break down this theorem or this definition just for you to get a little bit in depth about this. So we have a set x, which is a member of real numbers, meaning from negative infinity to positive infinity, and f of x, which is also a member of x, as this statement says, right? And we have an arbitrary value x naught that could be literally any value within f of x. So within the value of f of x, or within the graph of f of x, sorry, any x value that we choose could be our x naught. So the question says that, or the theorem, sorry, says that if we have a function f of x that is defined as set x that consists of real numbers, then it has the limits L at that x value. So meaning, for as much as we go, or let's just say we have our initial value of 1, meaning f of x is also going to be equal to 1, and meaning our limit is also going to be 1, because that's as far as we go. And this f of x is a limit or a whole at a point x naught when f of x is equals to L. So meaning it stops being continuous at that exact value of x naught. So meaning that's as far as we go. So if we have a function which is or our x naught which is 2, then our function ends at 2. Hope you get the picture. So if epsilon and delta are greater than 0, then there exists some sort of interval on both x and y axis. That f of x has got this type of notation where we have our limit plus our epsilon value, and then we have our limit itself, and then we have our limit minus our epsilon value, and then we also have our x values, which is x, and we have our delta minus our initial value of x, our initial value of x itself, and then we've got delta plus our initial value of x. This is all confusing and it doesn't really make sense or anything, so let me give you a visual representation. But before that, the whole point of this theorem is to understand the behavior of f of x as it approaches x naught. Like I said, limits help us understand the behavior, or to be able to observe the behavior of f of x when it reaches a certain value, right? So no matter how small epsilon gets, there will always be a point where x naught plus or minus delta exists, except at x naught. Note that L is undefined at x naught, meaning that this is not a theorem that involves continuity rather than approximates the values of a function closer to the limit, essentially observing its behavior as it approaches L from x naught. With numerical analysis, there's a lot of approximation here. We're not looking for the exact value, we are approximating the values. So we don't know what that value actually is at that point, but we are actually approximating what that value is, getting closer to it, but never at it. So this is what limits is, basically. And the value epsilon can also get close to L, but can never be L because f of x will be undefined. So let's have a visual representation of what I mean. I've talked about a lot of things, so let's just try to see what I actually mean. So let's just say we have our arbitrary point x naught here, and we have decided, hey, this is our point. And gonna have this type of relationship here. Oh, sorry. This type of relationship here, where our graph moves at that point and then it continues going, so on and so forth. So meaning we have our point L there, our point x naught, and as this graph continues going, it continues going until it reaches this point x naught, which is undefined, or L here. That's what this theorem actually means. And then we can have our limit minus our epsilon value, any value that we choose within this arbitrary range here on f of x, and then we say L minus our epsilon value, L plus our epsilon value, and we have x naught minus delta, and then x naught plus delta, and so on and so forth. It's kind of like this relationship that's there with limits. So I hope this graph helps you understand what we've talked about and everything that we've said and whatnot and everything. And don't worry, this is not as particularly something that you need to master in your head. What you need to master is the definition, actually, for numerical analysis when it comes to limits. That's the only thing that you have to master and you have to get stuck in your head. The rest is just fancy mumbo jumbo that's just there to confuse you. Alright, so hope you've understood the graphical method of what a limit actually is in this scenario. Alright, so let's talk about continuity. So we've talked about the concept of continuity, so now let's talk about the actual definition of a continuity. So this says that if f of x is defined in the set x of real numbers and x naught is also defined in the set x, right? So we have x, which is a set of real numbers, and x naught is defined within this set. Then we have limit as x approaches x naught for f of x is equal to f of x naught. So meaning whatever value of f of x naught we plug in, the function is going to be that at that particular point. Basically like a continuity, right? So this means that f of x is continuous in the set x if it is continuous on each number in x. So before we go to the graphical representation of what this actually means, there's a few things that I need you to understand. So we need the notation, which is we have c of x. This means that the set of all function is defined within set x, so meaning it's continuous on this function, right? So c means continuity. Wherever you see c, you see it means it's continuous. And we're going to be seeing that a lot during this theorem, so just bear with me. So we also have c, which is continuous on a, comma b. This means that the function is continuous within a given interval, right? And then r means basically real numbers. Okay, so if you have c is continuous on r or c continuous on this, it means that this function is continuous on a set of real numbers. Basically, we have that relationship, right? Okay, so let's have a graphical representation of what a continuity is. So let's have a function which is x naught, f of x equals to x naught, right? So let x naught be equal to 1. So if x naught is equal to 1, then f of x naught is also going to be equal to 1, as our theorem suggests, right? Our theorem suggests that if x naught is equal to a value within a range of real numbers, then our continuity formula is going to be f of x is equals to f of x naught. So meaning if x naught equals to 1, then f of x naught is also going to be equal to 1. And then within this graph, we're going to have that point there. If we have x naught and f of x naught, we're going to have 1 and 1. So we have this point there. And let's just say we plug in 2, where x naught is equal to 2. I think this is going to be 1, x1, supposed to be x1, sorry. But you get the idea. And we're going to have that point there. And if x naught or x2 is equal to negative 1, f of x2 is also going to be negative 1 as well. So we're going to have that guy there, and then same format with that guy. And then we have this type of linear coordination. And if we were to just join them up like that, we're going to have a graph that somehow resembles continuity of a function. So basically, we have continuity, which is defined in the set of real numbers and all that. This theorem is the same as what I was explaining earlier about continuity. But all you have to do is just master what this is, this theorem, because that's going to be very, very important later on. Alright, so let's go to differentiability. Now, this is a new concept that I did not talk about, but I'm going to talk extensively on it. So this basically deals with the derivatives of a function, obviously. And the theorem is, let f of x be defined within an interval containing x naught. Right? This function is differentiable if the derivative of f of x naught is equal to the limit of, as x approaches x naught, of this function exists. This is the definition, and if you just follow me, and I will explain to you exactly how this goes. So basically, if a function can be differentiated along a specific interval that is continuous, then f of x is differentiable on x. And basically, if we borrow the concepts of calculus 1, we get something like this. So we have this guy here, and then if we borrow the concept of calculus and everything, we're going to have limit as h approaches 0 for this. This equation, or this expression, is actually very important when it comes to proving differentiability in numerical analysis. You can use this concept because this concept and this concept are basically the same, but I'll show you later on how to actually solve for differentiability is in that case, because there might be questions where you might be asked to solve or prove differentiability equals to continuity and all that yada yada, and you just know how lecturers just want to test your thinking capacity. So I'm gonna prove differentiability implies continuity later on in this video, but right now I just want you to understand that this concept and this concept here are very, very important, and you should not miss them, not even for a single bit. So if you are asked in the exam or whatever you're going to be asked by a lecturer to define differentiability, this guy here is your definition or your theorem. This is just basically something that I want you to understand about. Okay, so as x approaches x naught can be referenced in the same way as h approaches 0. And we're basically looking for the derivative of f of x naught, giving a proper understanding of derivatives in general. So let me give you an example, right? So find f prime of a, right? If f of x is equal to 1 over x. So let's solve this. So step 1 is we've let f of x equal to f of a. Continue this guy here, f of x equals to f of a. So meaning whatever value of a, or whatever value of a we're gonna have, we're just gonna plug in x or vice versa, right? And apply the formula for f prime of a. Great. So f of a is going to be equal to 1 over a, right? We've seen that if f of x equals to f of a, then f of a is going to be 1 over a, and f of x equals to 1 over x. And we're going to say f prime of a is going to be limit as h approaches 0 for this type of equation there. Good. So step 2 is f prime of a, we're going to actually plug in this value here. So notice that I have said 1 over a plus h rather than 1 over something else. This might look confusing, but note that we are multiplying or adding this h variable to this a variable. We're not looking at a constant here because we don't know the value of h, so it's best practice that we add to the variable rather than the constant itself, to avoid any problems later on or down the line as we go on. So we have a plus h, um, which is 1 divided by a plus h minus f of 1 over a, as this function dictates, right? And then let's just remove the f's there, and then we're going to say f prime of a is equal to limit as h approaches 0 for this type of function, right? So we have this guy. So now let's simplify this expression. So getting rid of this h value at the bottom temporarily, that is, we just temporarily forget it. We solve for the numerator here, and then we have this type of equation here. So if we multiply, or we find the common denominator between this guy and this guy, we're going to multiply a by a plus h, of which you have this type of expression here. So we're going to say a multiplied by a plus h, which is being divided by this guy here. So we have this numerator and we have this denominator here. And then let's try to simplify this entire expression. So once we simplify this entire expression, we're going to say, okay, fine. If we were to subtract everything here, we're going to say a minus a plus h here, a minus a plus h, and then we're going to say a squared plus ah. Oh, for those who are wondering how I got to this stage here, we are basically doing fractions, right? I'm pretty sure you learned that in grade school. And a plus h here, we're going to divide this guy and this guy. So say wherever a plus h here, so there's a plus h there and a plus h there. So we're going to cancel those guys out. And then we're going to multiply this by that, right? So meaning this and this are gone, and then what's left is a 1. So we're going to multiply a by 1, and then we have a there, right? And then going to this second half of the equation, or the numerator, a and a here are common, so we just divide those two and get rid of those, and then we're going to have a plus h. And then we have 1 on top there, so we're going to multiply by a negative 1 there, and then we have this equation. And we're going to multiply these guys together, and we have a multiplied by a, which is a squared, and a multiplied by h, which is going to be ah, right? And then we have this type of relationship. Okay, so f prime of a is going to be equal to a minus h, right? So this is positive, this is negative, so these two automatically cancel out. And these guys, since they cannot be further differentiated or anything further, we can say f prime of a is equal to negative h divided by a squared plus ah. And note to self that this guy was omitted initially because we wanted to solve for the numerator first. So now that we've found our numerator here, we can plug it back in to this equation. And then we say f prime of a is equal to negative h, which is this guy, a squared plus ah, which is this guy in the bottom, divided by this h that we omitted earlier, and which is going to be equal to, or which is the same as saying negative h divided by a squared plus ah multiplied by 1 over h. And we have this type of relationship here where we have negative h on top and we have h here, so we just cancel these two out, and then we have f prime of a, which is equal to the limit as h approaches 0 for negative 1 divided by a squared plus ah. And if we plug in wherever h is, we plug in 0, we're going to have f of a is equals to -1 divided by a squared plus a multiplied by 0. And anything multiplied by 0 is 0 itself, so meaning the derivative of 1 over x is going to be equal to -1 over x squared, or we could say that 1 over a is equals to -1 over a squared. Notice that this is 1 over x, and this is the second, or this is the log of x, if you were to look at it in calculus form. So meaning the first derivative of log x is going to be -1 over x squared. Yeah, it's just something that I thought I could drop in later on. Alright, so hope you got a general idea of differentiability with that example. Okay, so let's go to actual numerical theorems. Okay, so we have Rolle's theorem, which is a very important theorem actually. Rolle's theorem and mean value theorem. These are two variations of the same thing. They talk about the same thing about differentiability. Once you've understood the concept of differentiability, that's when these numerical theorems come in. So let's get into it. If f of x is a member of a continuity of a comma b, of an interval a comma b, and f of a equal to f of b, then there exists a point c within that interval a comma b such that f prime of c is equal to 0, right? And just hold on, I'll explain this properly. Well, let's go to mean value theorem, which says if f of x is a member of a continuity a comma b, and f of a is not equal to f of b, then there exists a point c within the interval a comma b such that f of c is equal to f of b minus f of a divided by b minus a. So for Rolle's theorem and for mean value theorem, we have two different graphs that represent two different things. And then let me explain that to you. Okay, so we have f of x, right? Great. And if we say we have this type of graph here that goes into this particular setup. So we have f of x, or in this case, because f of x maps to a, so meaning this value becomes f of a. And then we also have this value that maps to b, which this becomes f of b. So meaning f of a and f of b are actually in the same line. So if f of a and f of b are in the same interval or are the same value, then there exists a point c within the interval a comma b such that the tangent of f of x or f of c is actually equal to 0. We get this point here, the derivative of this function at this point is actually equal to 0. Yeah, so our conditions are met where f of a equal to f of b, right? And if that scenario is within the required range or the specifications of that function, then f of c is going to, f prime of c, sorry, is going to equal to 0. Alright, so let's look at the graph for mean value theorem. But before that, we notice that this graph actually satisfies this condition, right? So let's look at this graph as well. So let's just say we have a graph that goes in this format, and then f of a is not equal to f of b, right? So f of a and f of b are not in the same line. Then we have a value c such that if we were to find the derivative of this function at the point c, we're going to have to use this formula here. And then we're going to make sure that this point and this point are parallel to each other. And it's some kind of relationship that we have here, right? So we have Rolle's theorem and mean value theorem, and then these are their respective graphs. Hope that actually helps you understand the difference between what Rolle's theorem is and mean value theorem is. So whenever you have a function where f of a and f of b are the same, you can use Rolle's theorem. And the mean value theorem when these two are not typically the same. We have another concept we have another theorem, sorry, in numerical analysis, which is called the intermediate value theorem. And the theorem states that if f of x is a member of a continuity between a comma b, and let k be any number between f of a and f of b, then there exists a point c within the interval a comma b such that f of c is equal to k. So what that basically means is that we pick any number on the y-axis between f of a and f of b, and if that number within f of a and f of b exists, then there also exists a point c within the interval a comma b such that f of c is equal to the number you picked. Let me show you. So we have this type of graph here, right? And then we have this graph going in that type of way. And then we have f of a, and then we have f of b. So if we were to pick any arbitrary value k within f of a and f of b, right, then there exists a point c within this interval here such that f of c is equal to that actual value itself. We get the picture, right? At least we have that type of relationship. So this is basically the visual illustration of what intermediate value theorem is. Alright, so understanding that, understanding the graph, I hope you have a deeper understanding of this theorem itself. So we also have extreme value theorem, and this deals with 2 points, a lower point and a higher point. So we have a point within a graph that is higher than f of x, and we have a point that is lower than f of x, right? But then the actual theorem states that if f of x is a member of a continuity a comma b, then there exists 2 points, x1 and x2, or x0 and x1, which are members of a comma b, such that f of x1 is less than or equal to f of x, and which f of x is less than or equal to f of x2, right? So basically what this means is that if f of x is differentiable on a comma b, then x1 and x2 occur at endpoints of the interval a comma b, where f prime of x is actually equal to 0. So here is the actual graph. So we have a and b, and we have this type of function, right? So we call this f of x. Great. So if this is our f of x function, we have our point x2 and x1, right? So in this scenario, we have x1, which is our lower limit, and we have x2, which is our higher limit. This is how the graph goes, but initially you can't have x2 and x1 there and all that. But for purposes of illustration, just go with the flow here. So we have f of x2, which is the highest point of f of x, which this means that f of x is greater. Sorry, f of x2 is greater than f of x, right? And then we have our lower limit, which is f of x1. So we have this type of interval where f of x1 is less than f of x, and f of x is less than f of x2. And then we have our points where f of x at that particular point, so we say f of x2, the derivative of that is 0, and f of x1, the derivative of that is also 0. So there is this relationship that about everything, and then with extreme value theorem, where you have 2 points within the interval, and then at those 2 points, the upper bound and the lower bound exist within that interval of those 2 points. Okay, so I hope that clears out a few cobwebs when it comes to extreme value theorem. Alright, so earlier on I said that I'm going to explain differentiability implying continuity, and this is the exact example that we're going to use. So just follow me step by step, and we are going to go through this, and I hope that you understand what this actually means. Okay, so proving that differentiability implies continuity, first we have to show what the definition of each is. So the definition of a continuity, what we're trying to prove here, is limit as x approaches x naught for f of x is equals to f of x naught, by definition, right? So when proving something, we first have to know what we're proving here. So first we have to know what continuity is, then we know what differentiability is. When we know the two, then we can actually find some relationship between the two. So a continuity implies that the function f of x is continuous at a certain interval a comma b. So let f of x be defined within the interval a comma b. Therefore, f of x is a member of a continuity between a comma b, right? Good. So next we show what differentiability is. So by definition, differentiability means that f prime of x, or the derivative of f of x, equals to the limit as x naught, as x approaches x naught, for f of x minus f of x naught is equal to x minus x naught, exists if and only if f of x is a member of a continuity of a comma b. So we have let f of x be continuous within this interval, right? So meaning we have satisfied this condition. So if this condition exists, the meaning this condition also exists, right? Good. So now let's get into the actual proving. So let f prime of x be equal to this guy here, right? And then if we prove by contradiction, say if it is not continuous on a comma b, then the opposite of a continuity is a limit. Therefore, we're going to plug in the opposite of what a continuity is, and we also have to plug in the definition of what a limit is. So we have f prime of x, which is equals to limit as x approaches x naught for f of x minus f of x naught divided by x minus x naught, which is equal to limit as x approaches x naught as f of x is equals to L. So if we were to take away these guys here, or these f of x's here, and then factor out the limit as x approaches x naught, this one and this one are the same, so we can just plug this guy all the way over here and say limit as x approaches x naught for the function f of x minus f of x naught divided by x minus x naught is equal to limit, right? Great, because we have said that if it is not continuous, then it has an asymptote, meaning it is not continuous, meaning it's a limit. It has a limit, right? Great. So now we say this guy here, and then we say limit as h approaches 0. Remember, I told you that this guy and this guy are practically the same thing. So limit as h approaches 0 for f of x plus h minus f of x naught divided by h multiplied by limits, right? So we have this type of scenario here. Okay, so if we have that, then we're going to multiply this h by L. So if we multiply these two together, we have L multiplied by h, and then we also have f of x plus h minus f of x naught. Great. So now we cannot further differentiate, or we cannot further break this down or factorize this expression. So if we can't do that, then we just plug in wherever h is, we plug in 0. So we have this type of equation now. When you plug in 0, where f of x plus 0 minus f of x naught is equals to L multiplied by 0. So this equation here, or this part of the equation, becomes 0. And then we have this f of x minus f of x naught. And if we have f of x minus f of x naught, notice that there is a negative value there, and we can plug this guy on the other side to make this guy positive, and we say f of x is equal to f of x naught. So we have gone through step by step on how to actually prove differentiability equals to continuity. And we've proved by contradiction, saying that, hey, this function is not continuous, so meaning therefore it's a limit, right? And if it has a limit, then we have proven, say, we have seen that, but when we actually solve this, we see that we get a continuous function. Therefore, this function must be continuous. And we have gone from differentiability all the way to continuity. Notice that we've gone from this equation all the way up to this equation, which is equal to this guy. So we've gone from this guy to this guy using this type of scenario. So everything on your screen right now is practically important when it comes to proving differentiability implies continuity, and so on and so forth. I hope this helps you understand what differentiability and continuity is and everything that it deals with. Okay, so finally we are going to talk about a calculus itself. Right, so these are cheat codes that I wrote specifically for you guys. In case you're not really good at calculus itself, because for the next couple of videos we're going to be using everything that I'm going to show you in those videos. So because it's a course that involves calculus, there's some important information that you might find useful. So we've got calculus cheat codes, and let's get. So working with exponents and logarithms in calculus. So the basic rules of calculus that we're going to be using for majority of this course are basically four. We have a constant rule, we have a power rule, and we have chain rule, and we have a quotient rule, right? And with these guys here, I think you can just pause the video and you can just write this down. This is going to be very important. On the top here are the concepts of the four rules that I've given you on top, and then on the bottom are the examples of these rules. So it just gives you a feel of everything that you're going to be experiencing in numerical analysis. So you can pause the video right now and you can just write this down. Alright, so I'm assuming that you've written this down, so we can go to the next set, and exponents and logarithm cheat sheets for using those concepts that we learned in calculus. So e to the power x, right? E to the power x, the derivative of this, you can find it by using this format. So you have the derivative of this function here. Note to self that this is a function on the top here, right? So this is u of x, right? So this is a function on top here. So we're going to say e to the power u of x is equal to e to the power u of x multiplied by the derivative of this function on the top here. And then we see that the derivative of this guy is just that guy. And the derivative of x is always 1, right? So 1 multiplied by this function is going to be this. So for as many times as you are going to get e of x, or finding the derivative of Euler's number to the power x, you're always going to get this value, right? Great. Oh, note with a constant like pi. So if you were to find the derivative of Euler's number itself, then you are going to get 0. The derivative of Euler's number without an exponent here is always 0. Just so to just catch up to speed. And you can also have these logarithms here, and finding the logarithm of any x value or the derivative of this guy, you use this formula here, right? And you can just copy this, and yeah, so that's it with numerical analysis. Next we're going to talk about solutions to function in one variable, which are also numerical methods. And with those, we talked about it in our introduction video, which is bisection, Newton-Raphson's method, and secant method. And we're going to go in depth with those methods, and hopefully you understand what everything goes by in those videos. But for now, I bid you farewell, and I'll see you in the next video.